All right, so we're changing from talking about exponential growth to exponential decay. And of course, the only thing that's really different in the model is the negative sign in the exponent. So this model tends to be used in things like carbon dating, the decay of radioactive substances, things like that. So here we're going to have a sample of krypton 85, which has a continuous decay rate of 6.3% per year. What's the exponential decay function, right? And so we're looking at, so our amount of krypton 85 is however much we started with, which this didn't tell us, e to the negative 0.063 t. All right, let me write that bigger. So P0 e to the negative 0.063 t. That's all that there is to the exponential decay function. And of course here now P of t is representing the amount of our substance that's left at any given time. P0 is our initial amount, and K is our decay rate. But all of these are important. We want to make sure that we know that it's continuous decay. All right, so here the amount of carbon-14 present in animal bones is given by this equation, P0 e to the negative 0.00012 t. So P of t is giving the amount of carbon present after t years. Find the age of the mummy discovered in Egypt if it has lost 46% of its carbon-14. So if it's lost 46%, that means it has 54% remaining. Right? So from that we can say, okay, great. I have 54% of whatever I started with, which we don't know what it was. And now we can solve this thing for t because P0 is going to divide out. So you do not always need your P0, your starting amount, to answer these types of questions. So we're going to divide out the P0. We've got 0.54 equals e to the 0.00012 t. How do we get the t out of the exponent? You say, we're going to take the log of both sides. So I take the log of e to the negative 0.00012 t. I use my power rule to bring that exponent to the front. And then I say, oh, but ln of e is 1. And so now I can get my t just by dividing both sides by the negative 0.00012. And of course, ln of 0.54 is going to be negative, right? Because if we think about the graph of the natural log looks roughly like that. This is the 0.10, so we know ln of 0.54 is going to be negative. But we've got to throw that in our calculator here. 0.00012. All right, so this mummy is 5,134. We'll call it 5135 years. All right, so not too bad here. So similar to doubling time is half-life, and you've probably heard of half-life in conjunction maybe with chemistry class. We talk about, radioactive decay and things like that. So the half-life of a substance is the amount of time it takes for 1/2 of the initial amount to decay into some other isotope. So in other words, it's the time for P0 that it takes for the initial amount P0 to become 1/2 of P0. And so same story as before, we can say, okay, great, I can cancel out my P0s. I can take the natural log of both sides. So the power is going to come around front, so negative kt ln e, but that's equal to 1. Now, ln of 1/2 is the same as ln of 2 to the negative 1, right? Which is then negative ln of 2. And then we can solve for t by dividing both sides by negative k. So we get ln, so the negatives cancel, and we get exactly the same formula that we did for doubling time. right? ln2 over k. There we are. So we can do this last one. We can do this one, and then there's a longer example that will be our last video officially on 6.7. So we're told the continuous decay rate of iodine 131 is 9.6% per day. What is its half-life? So we're going to say, okay, great. I remember that's ln2 over k. So ln2 over 0.096. We've just got to throw that into the calculator because I don't know what that is. So I got ln2 over 0.096 is going to tell me 7.220283, but we'll call that 7.22. So, and the units on that one are going to be days. So after just over a week, you will have half of what you started with. All right, so this is a homework problem. We will put that in its own video.